So, last time, can you see this? So we were talking about the weakly interacting Bose gas. Okay, so the Hamiltonian was sum over k, k squared over 2m minus mu, a dagger k a k plus 1/2 omega sum over q rho q vq rho minus q, where rho q was 1 over omega sum over k a dagger k plus q a k. This is the density operator and second quantization. Then what we did is we used mean field theory to seek. We know from we know that without this interaction, just the free gas undergoes Bose-Einstein condensation. Now we want to understand that with the interaction in the interacting model. We know that for the Bose-Einstein condensation, A assumes an expectation value, A0. A0 means the occupation, so the dispersion of these particles. This is the dispersion, right? This is epsilon of k. This is k, and we're talking about massive occupation of the zero energy state. So we assume that A of 0 is equal to A dagger of 0 is equal to some square root of n0. This is basically what we assume. N0 is the number of particles in this zero state. And then we use this to decouple the Hamiltonian, write the Hamiltonian in quadratic form. We neglected fluctuations around this solution up to quadratic order. So we get k squared over 2m minus mu k, a dagger k, a k, plus sum over k not equal to 0, rho naught vk over 2, a dagger k, a minus k dagger, plus a minus k, a k, minus rho naught omega v naught over 2. And this mu k guy was defined to be mu minus rho naught v naught minus rho naught over 2 v of k plus v of minus k. Okay? Then we use the Bogolyubov transformation to diagonalize the Hamiltonian. We use a Bogolyubov transformation. Okay, so we define a new operator alpha k, which is uk ak plus vk a dagger minus k, and we saw that in order for alpha k, alpha dagger of k to be equal to 1, okay, from this we concluded that uk squared minus vk squared is equal to 1, which implies that these are most conveniently represented as sine and cosine hyperbolic functions. And under this assumption, we obtain that we can choose UK and VK, which I'll write in a moment, such that the mean field Hamiltonian will become EK alpha dagger K alpha K plus a ground state energy. So this is now a quadratic Hamiltonian. It's only up to mean field. What these guys represent is what we call quasi-particles. Okay? So the idea is that we start with an interacting Hamiltonian. Okay? And presumably, and one needs to check, and there are ways to check that if these excitations exist, they represent quasi-particle excitations. These are called Bogoliubov quasi-particles. And the idea is that at the ground state, you occupy none of these guys. By the way, this K is of course not equal to 0. It only represents the K not equal to 0. And you can excite these Bogoliubov excitations. Each one of them comes with an excitation energy EK, which I'll write in a moment. But in the absence of them, we have a ground state energy. And then we saw that UK is equal to the square root of K squared over 2m minus mu K divided by 2EK plus 1/2. And VK is equal to K squared over 2m minus mu K over 2EK minus 1/2. EK, the excitation spectrum was K squared over 2m minus mu K squared minus rho naught squared VK squared. And the ground state energy is omega 1/2 rho naught squared V naught minus mu rho naught minus sum over K not equal to 0 1/2 K squared over 2m minus mu K minus EK. Okay? And then what I claimed is in order to complete the mean field analysis, we want to know what is this N naught, or if you like, by the way, I forgot to mention that rho naught is just N naught over omega. Omega is the volume, so rho naught is the density of the condensate. Okay, so this is the number, the occupation number of the condensate divided by the volume. It gives you the density. And then the last statement was that we have two parameters that we need to solve for self-consistently. One of them is the chemical potential, and the other one is the order parameter rho naught. So what we want to do is we want to take the H, the full H minus, or okay, so yeah, maybe okay. So we can do this in two ways. I'll just quickly describe. So one of them would be to assume that we can compute something like AK, A minus K. Oh wait, no. Okay, so probably what we need to do is, the best way is to compute H within the mean field minus TS, which is another story, and take a derivative with respect to rho naught equal to 0. Okay, and the second one would be that N0 plus sum over K dagger, sorry, not K dagger, K not equal to 0 A dagger K, A K, expectation value. This whole thing is the total density. So this equation fixes mu. This equation will fix rho naught for finite t. And this is a whole business to itself because, you know, we need to compute the entropy. This is like free energy. This is a whole story, which we're not going to get into. But at least at zero temperature, we can say something quickly. Because at zero temperature, this term doesn't contribute. And the expectation value is just the ground state expectation value. And then what we saw, so this is basically more or less where I stopped last time. Okay, at t equal to 0, the first equation becomes dE ground state to d rho naught equal to 0, and if we assume a contact interaction, meaning that v of k is equal to v naught, we will denote it by v naught. Basically, it means that in real space, we have a delta function interaction. In momentum space, we have a constant interaction. Then in this case, we get that E ground state is approximately rho naught V naught minus mu. And from here, a rho naught squared, 1/2. This is a mistake I forgot to correct. And therefore, dE ground state to d rho naught gives us rho naught V naught, this is rho naught, minus mu equal to 0. Therefore, what we find is that rho naught is mu divided by V naught. That's one solution. And then we can also plug this in EK, and what we found in EK is that this gives k squared over 2m plus rho naught V naught. I'll probably give away an exercise where you can do this yourselves and see that it works, just to that, you know, in case you don't believe me, k squared over 2m plus 2 rho naught V naught. Okay, this is basically what we obtain. So what this implies, what does this imply? Okay, this implies that these Bogoliubov excitations, it looks like some special case where, you know, it's weakly interacting and it's a contact interaction, blah blah blah. In that case, we obtain that this EK, the excitation spectrum of these Bogoliubov excitations, is basically linear, and then it transforms to quadratic. Okay, and we can also plot, you know, the chemical potential as a function of some parameter, like maybe temperature, whatever parameter it would be, and basically what we expect is something like that. And then we see that if we plot the order parameter, let me bring another color, maybe let's try 60. Black works. Say you take the square root of n naught, it's basically 0 up to this point, and then it does something like that. Okay, that's what we see. So this is one comment. Another comment is that this is weakly interacting. And then if it's strongly interacting, it's also going to be linear, but it can have something we call a Roton minimum. Okay, so all this is what we saw last time. Okay, so this is very insightful. It allows us to obtain many results accurately. It's also quite, you might be, I'll let you solve it at home and you'll see that it's quite annoying. Like it's an annoying calculation because you have to do it very carefully. There's a lot of operator formalism. There's a lot of math. So now I want to look at this from the point of view of field theory. So first of all, you're going to see that in field theory description, everything is much easier. That's one thing. But another thing which is much more important is that it might have looked just like magic that at this solution, the dispersion happens to be linear. But actually, there's a very deep reason the dispersion is linear. That's what we're going to talk about today. So I'm going to write path integral formalism approach. To the Bose guess. Any questions about before we start? So what we're going to do now is we're just going to take the Hamiltonian I wrote in the beginning of this lecture and imagine that when we derived that field, this path integral formalism, that was our Hamiltonian. So what is the action we're going to obtain? What is the action going to look like? Someone wants to read it out to me. So let me write the Hamiltonian. The Hamiltonian is here. H of A dagger and A. The operator, I'll write it again. It's a sum over K, K squared over 2M minus mu, A dagger K, A K. Okay, plus 1 over omega, sum over k, k prime and q. Or maybe actually, no, let me write it in a way that will be easier for us. An integral d3 r v naught a dagger r a r squared. Actually, let me do this also here. It will be easier for us. Is there a question? Question?
No.
So this is the Hamiltonian. Okay? So now tell me, what is going to be the action?
The integral of the time.
So we have an integral over time.
Tau.
Tau. It's imaginary time. Okay? Between 0 and beta. And then we have, what do we have next? The integral over space.
I.
ddr. Whatever. What?
So this is the Hamiltonian text.
Yeah, this. No, this is the full Hamiltonian.
Okay.
Okay? And then what am I going to have? You don't know?
I omega.
I omega? No, we're writing it in real space. And real imaginary time, if there is such a thing.
Psi bar.
So we're going to have psi bar. Okay, good.
Bracket.
Yes.
It's minus tau, derivative with respect to tau.
Okay, d tau.
Then minus
Mm-hmm.
the psi
The what?
and Well, the
Here.
Yeah.
Okay, and then what? Then I have the interaction. So, and then the interaction is going to look like V naught V naught over 2. Actually, there should be a factor of 1/2 here. Never mind, that's just due to the self-interaction. So we subtract the self-interaction, and then we have psi to the 4th. Okay, so this is the action that we want to study. Okay, so this is the action of the weakly interacting Bose gas with contact interaction, equivalent to the mean field that we just did. Okay? So you can notice that we can basically treat, so these two are derivatives. Okay? We can look at the other terms, terms that are proportional to psi absolute value, like potential energy. So let me do that. So let me define U of psi squared. Okay, this is the potential energy, as minus mu psi squared plus V naught over 2 psi to the 4th. Okay? And if I draw this potential, then I find that, look at this plot here. So this, what separates this low temperature regime from this high temperature regime? That this should be
defined.
What happens here as opposed to here? What is the difference?
There are excitations of the
What?
There are excitations of the Mercurial particles.
Okay. Why? What happened?
It's phase obviously.
Yes.
Because the interaction becomes relevant. Right?
Well, it's not that, but in much simpler words. It's not superconductor, it's a superfluid. This is superfluid. This is normal. Okay? So this is the transition from the normal to the superfluid. So I see that when I'm in the superfluid phase, mu is positive. When I'm in the normal phase, the mu is negative. Okay? So let's see the equivalence in the field theoretic description. So what we see is if I plot this u of psi squared as a function of the imaginary of psi and real of psi, okay? Then in the case where mu is smaller than 0, okay? So this is the normal phase. Okay, in the normal phase, this looks like we basically have like a k'ara, like a bowl, okay? And the minimum of the k'ara is at 0. On the other hand, okay, when mu is greater than 0, this is the superfluid phase, this potential looks different. It basically looks like this. Okay, so I don't know if the drawing is clear, but it's basically has like a minimum that sits on a ring, and the radius of this ring is what?
Where the north of me, yeah.
It's what? Can you read it from here?
So
how do I?
The square root of maybe mu over v0.
Yes. So this is exactly square root of mu over v0. And if you'll open your notebook, what we wrote for the mean field solution was exactly this. It was mu, right? Mu was equal to v rho naught. That was the solution. Okay? And therefore the order parameter square root of rho naught is exactly mu over v naught square root. Okay? So first of all, we get the same thing. Okay, I can summarize it here. The psi squared, which is like our rho naught, is basically 0 if mu is smaller than 0, and it's mu over v naught when mu is greater than 0. Okay, so we get the same thing. So up to now we're happy. This looks very familiar, but now we're going to see that we can gain much more insight about this from this perspective. So, and in particular, what we want to do is we want to think about the superfluid transition as a symmetry breaking transition. Okay, so the superfluid transition as symmetry breaking. So if we look at this action, okay, you'll find that it has all sorts of symmetries. Okay, so for example, it's translationally invariant. Okay, so if we make a translation, it remains invariant. There is nothing here that depends on position. It's rotationally invariant, same idea. Okay, but it also has one additional symmetry, and that's the symmetry that's important to us. Okay, so the action, maybe we can denote it. Let's denote it by star. Star has multiple symmetries which I mentioned. So let's focus let us focus on a particular one which is broken in the superfluid phase. Okay, and this symmetry is, someone wants to guess what symmetry is broken in the superfluid phase? What symmetry that exists in the original Hamiltonian is destroyed in the superfluid phase? Particle hole symmetry. Yeah, I don't know. So particle hole, if you say particle hole, what that means in field theoretic description is basically exchanging psi and psi bar, which so before, first of all, no, I don't think it's a particle symmetry, but maybe it will help you to think about what this symmetry breaking, like what the ground state of the system actually looks like. So here you see the minimum was at 0. But here, what is the minimum? The minimum is actually a circle of points. Okay, so the order parameter needs to choose. We need to, it's like, think about a magnet, for example. Okay, let's take the Ising model. In the Ising model, you have two configurations for the spin state. They're either up or down. Now, once they become ferromagnetic, they're not in a superposition of up and down, right? Although quantum mechanically they can be, and we can discuss later why they wouldn't be, or what that means to be in a superposition. The same thing happens here in the superfluid. It doesn't obtain superposition, and we'll discuss that later. Instead, it chooses a direction. This is a very deep concept. It's non-trivial, but it's similar to the Ising transition. The Ising transition, it's either all the spins are up or all the spins are down, and there is degeneracy between these points. So it could have equally chosen, say, to be up or down, but it has to choose one of them. So in this case, it has to choose a point. Right? We have to choose, you see there's a circle here, there's a minimum, and I have to choose a point. Like the order parameter would be, something like a rod. So it's defined by an angle, which is the phase, and the magnitude, which is basically fixed by mu and v naught. Okay, that's clear? So now that I told you this, can you guess what the symmetry that is broken here? You have a good guess? Rotation? Rotation, you mean spatial rotation. So this space is not real space. This is the space of order parameters.
Phase.
What?
Phase symmetry.
Phase. What is it? So, yeah, phase is correct. We just have a fancier name for that.
It's a gauge invariance.
It's global. It's not just gauge invariance. It's global gauge invariance. Okay, global gauge invariance. Okay, so what do we mean by global? Global means that it's a constant. So it's something like this. Say you have psi, and under the transformation, you go to some psi prime, which is e to the I theta, okay? Psi, and theta is a const. Okay, it's the same everywhere. Okay? Now, why is this Hamiltonian invariant under this? It's invariant because everywhere where you have psi, it's also multiplied by psi bar. Okay? And these derivatives, because this is a constant, it doesn't matter for them. Now, do you remember why every psi comes with a psi bar? Where did that come from?
From the conservation of particles.
Yes, exactly. Exactly. Because as long as we have the same number of psis and psi bars in each term in the Hamiltonian, it means that each term in the Hamiltonian destroys and creates the same number of particles, meaning that the total number of particles is not changed at the action of the Hamiltonian. So that means that the Hamiltonian, or in other words, the Hamiltonian commutes with the total particle number. So this tells you that this global gauge invariance, and we'll see that more in a moment, is related to number conservation. Okay? So the fact that there is a conservation law means that there is some symmetry in the Hamiltonian. This is basically Noether's theorem. And in this case, the one that is associated with number conservation is global gauge invariance. And this is the symmetry that's broken in the superfluid phase. You wanted to ask a question?
Why we can assume that in the normal phase there is a
Number conservation?
Yes.
We don't. First of all, you don't have to assume that. For example, if you open the, you know that in the web, like in Twitter or I don't know wherever, it's very fashionable to flash this the Lagrangian of the standard model. Wow, look at this! It's such a long equation. Blah blah blah. Okay, I'm smart. If you look at that, you'll notice that the bosonic fields in the theory, they appear to first order. Like A appears in linear order. That's how it couples to matter. So indeed, the number of photons is not a conserved quantity. Okay, so the ground state of the standard model, or at finite temperature, whatever you want, it's not it's not a wave function that, you know, all the different superposition of states has the same number of particles. It's going to be a superposition of, you know, states with 3 photons, states with 4 photons. You see, because there are transitions, because the reason is because an electron can emit a photon or absorb a photon, and therefore photons under the general terms in the Hamiltonian, the photon number can change. And this tells you another deep thing, indeed, which you might that in order to have this kind of superfluid transition, you need number conservation. You need models that have number conservation. So indeed, if you take you know, if you somehow have interacting photons, okay, you can make photons interact, or interacting phonons, and you cool them down, they're not going to become superfluid. They're just going to disappear. Okay? Wait, just to conclude the thing. But if you take bosons that are conserved, like helium-4, for example, that's matter. It doesn't disappear or create, or, you know, form out of nothing, and therefore it can it has this symmetry, and it can break it, and you can have this phase.
So it's like it's come together. As long as the boson number is conserved, we can make it a superfluid.
Well, as long as the boson number is conserved, you cool it down, potentially it will become a superfluid. So this is, if you like, this is even the model that, you know, this is the reason why we looked at this model. And by the way, there are models of particles where the number is not conserved. For example, downstairs, or even in this floor, Lev Chaikovich has a lab. In the lab, he is using laser fields to cool down atoms. If you'll walk, by the way, in the corridor, on the left and the right, Ofek made sure that the whole corridor is filled with the Nobel Prize posters, if you notice. And on the left, there is a Nobel Prize for the first BC. It was obtained in Boulder, Colorado. It looks like a three-dimensional plot where you have this spike. You know, that's the momentum. They have a way of imaging the momentum distribution of the Bose gas. But it turns out that there the number is not exactly conserved, because there are processes where two atoms collide and create a molecule. And when they do that, you know, their kinetic energy, so the molecule is lower in energy, And in order to conserve energy, that it needs to have some kinetic energy. So, and also the whole trap is not built for these molecules, it's built for the atoms. So effectively what you have is that you have processes where atoms collide and disappear. So there you have, for example, a question. So for example, my advisor, when I was doing my PhD, was investigating this question: do you still have a superfluid transition if you add these processes? And it's basically becomes a non-equilibrium problem, where you can have particles disappear as you're going along. So that's a whole question to itself. But specifically here, we want to think about some sort of matter field, and it's also a path for superconductivity, because superconductivity, I remind you, is a phenomena where these bosons are pairs of electrons, and electrons are definitely conserved; they don't disappear. So this is another maybe answer. Okay? So now we're going to make a few comments. Maybe we can, do you want to go on a break now, or shall we continue a little bit more? No comment? Maybe we'll go for another 15 minutes and then we'll have a break. Okay? What? Okay. So a few comments. So the first comment, so just to make this a little bit more clear, what this implies is that the order parameter, right? We said that this is the order parameter. The expectation value of psi takes a finite value. So if I draw, if I'm looking at this in this space of imaginary of psi and real of psi. Okay, I'm looking at this, and here I have this this ring, which is all the degenerate minima of this potential. So this radius is square root of mu over v naught. Okay, and this angle is theta. Okay. Then the psi, okay, psi is exactly this complex number here, okay, and this guy is not equal to psi bar. This is basically the statement that it's exactly like saying that, if you have an Ising order parameter, you have up, it's not equal to down. One is plus and one is minus. But here the difference is that it's not just two degenerate minima. It's actually there's a continuous symmetry, and therefore there is an infinite number of degenerate ground states. Each one of them is a different angle.
Yonathan, it's psi bar or psi tag?
No, this is psi tag. So psi tag is transformed.
Okay.
You see, it's a gauge. This is a global gauge transformation. So what I'm saying is that when you look at the order parameter, so again, let's take the Ising model as an intuition. If you take the Ising, you have a symmetry of flipping all the spins. The Hamiltonian remains the same. Mm-hmm. That's the symmetry that's broken, either up or down. So if you take the order parameter up and you apply this symmetry on the order parameter acts non-trivially. It flips. Same thing here. The order parameter, if you act on it with a symmetry, it changes. This is the idea. This is, by the way, when you choose an order parameter, this is actually the essential ingredient, that the symmetry that it broke acts it non-trivially on it. That's by definition. Okay, so that because this is a continuous symmetry, then we know that no ether theorem tells us that for each continuous symmetry, there is a conserved current. Okay, so here we have a continuous symmetry. What is the conserved current? So to that end, let's think of the transformation again. So the transformation, as we wrote it there, is something like this, which, if we think of this theta as like a small transformation, so theta much smaller than 2 pi, right? This is how we construct the Noether current. Is psi is something like 1 plus I theta psi, and therefore psi bar
Psi prime bar?
yeah, maybe let's denote this by prime. Psi prime bar is 1 minus I theta psi bar, okay? And then I'm writing the current. So this is the 4 momentum, okay? So the 0 component is delta S to delta d tau psi bar, d psi bar to d theta, okay? And plus delta S to delta d tau psi, d psi to d theta, and this thing becomes I times psi bar psi. I, yes, okay. And the spatial current is delta S to delta gradient of psi bar d psi bar to theta plus delta S to delta psi d psi theta, and this guy is minus I over 2m psi bar grad psi minus psi grad psi bar. Okay? So do these two look familiar to you? What is this? Density.
The density current.
And what is this?
It's current.
Density current.
Yeah, it's probability. Probability or density. It's so from here we see that the conserved quantity, right? The conserved quantity is d mu j mu. Okay. Then we get basically something like I d tau psi bar psi, right? Minus the gradient of 1 over 2m of this psi bar gradient psi minus psi gradient psi bar. Okay, this thing is equal to 0 is basically just the continuity equation. So, and that's not surprising. It's telling us that this indeed that this continuous symmetry is related to number conservation. Because we have number conservation, then the conserved current is the continuity equation. Because if you remember the derivation of the continuity equation appears anytime we have a conserved quantity, that conserved density that doesn't disappear. Okay, so that we've said enough about. The second comment, what?
Where you calculated the JFS and J vector, don't doesn't it mean to be psi prime a bunch of times there?
Psi bar a bunch of times
Right.
there. Yeah, I guess you could call this psi bar. Also, there's probably a factor of 2 that I'm missing there, but never mind. Okay, the second comment is that the superfluid transition demonstrates a deep concept which is a continuous transition leading to a non-analyticity. Non-analyticity related to symmetry related to a change of symmetry, to a change of symmetry. Okay? So here I want to kind of quickly go through 2 possible transitions we can imagine. One phase transition where symmetry changes. Okay, so I'm looking at phase transitions. Okay? And then I have without symmetry, without a change in symmetry. Okay? And the second one is with a change in symmetry. So without a change in symmetry, what we typically have is we have a situation like this. We have some free energy or action or whatever, and we have 2 minima, okay, A and B. And then as a function of some parameter, we go to a second state which looks like this. Okay? So this is the space of configurations. This is like the relevant potential. This is the space of configurations, and these are 2 phases, phase A and phase B. And if phase in A and B are not different in their symmetry, then you generally have a first order transition. Okay, this is exactly what you know in which transition? In what? No, ferromagnetic transition breaks the symmetry. The most well-known phase transition. What? Van der Waals, yeah, but Van der Waals describes the water to vapor transition, right? Okay, so liquid vapor transition is like this, and indeed it's typically first order. Okay, and the reason is because how can I explain this? There is no nothing. Okay, one way of thinking about it is that you can add a linear term to your free energy, which couples to the order parameter. So imagine that I have some tuning parameter. So let's call this some field phi. I don't even know what it is. Okay? Because there is no symmetry between A and B, I can add a term that looks like, say, alpha minus alpha phi. Okay? And then as I tune this alpha, I can just push this, the B minimum with respect to the A minimum. And just push them. It's allowed. So generally what you have is because this is allowed, it will generally appear. Okay? And because it generally appears, you typically have these minimums crossing. And you have these first order transitions. On the other hand, here, what we have is the simplest, let's put it this way, the simplest case with symmetry is something like this. Like we saw. Okay? So this is like A1, and this is like A2, and they're symmetric. Okay, this is what we had, and this is basically 0. Now it doesn't have to be like this. Okay, so what I have here is something like delta F is equal to minus alpha phi squared, which is like our mu term. Now, why can it only come at level of phi squared? Because if there is a symmetry, okay, then phi can't appear linearly. Right? Phi is like our order parameter, if you like. So phi goes to minus phi is not breaks the symmetry. So we can't break the symmetry explicitly, so this is the only thing that can appear. And therefore, you generally have this kind of transition. Now, it doesn't mean that it has to happen. You can have a first order transition due to many different effects. So for example, sometimes you can have that the fourth order term becomes negative. So you can have situations, maybe I'll plot it here. You can have situations where the minimum around 0 is actually positive, okay? But then you can have like the fourth term, and then these guys can cross 0 and give you a transition from 0 to some finite value. So you're going to have a first order transition. That's allowed, okay? And it's symmetric and everything's fine, but you see that this is just more complicated. This requires like extremely large fourth order term, and typically the simpler things happen in nature. And therefore we see that symmetry breaking transitions are often second order transitions. And non-symmetry breaking transitions are typically first order transitions, just because that's the simplest thing that we can write. Okay? Okay, maybe now it's a good time to go on a break, and then we'll summarize. I'll summarize to you everything that we're going to see and what this implies for what's going to come. Okay? Okay. We will establish. What I want to say now is that in what will follow, we will reach the following, or we will establish the following concepts. Okay? Now, why am I stating them? I just want it to be, clearly explained. So the first thing is that the excitations above the symmetry breaking ground state are gapless and linearly dispersing if the symmetry is continuous. Okay, this is known as Nambu-Goldstone theorem. Okay, so this is the first thing. Okay, so the fact that we broke a continuous symmetry spontaneously means that there is going to be a linearly dispersing mode. We already saw this linearly dispersing mode. These are the Bogolyubov excitations. But now we're going to establish the fact that there is a deep reason which is related to this symmetry breaking. Okay? And if you want intuitive explanation, then let's again look at our ground state. Okay, so imagine that we chose a certain theta. So this is like the ground state, but I can imagine exciting it by changing theta from position to position. Okay, so imagine that I create a wave configuration. Okay, well later we'll derive this explicitly, but let's say this is like position. Okay, and now I slightly change it as a function of position. So you see, it is slowly changing its orientation. Okay, and this is like, like a wave. Okay, so you can imagine that in the limit where you take q to 0, right? Here q is maybe let me make this a little bit clearer. So imagine that now I start bringing it back, and here it goes all the way back. So this is basically like a wave. Okay, what I drew here is kind of like a wave. So if I plot theta as a function of x, then it basically starts from some value. Okay, there is some value theta 0 here, and then it kind of grows. Okay, and here it kind of goes back. Okay, so this distance is like pi over q, right? This is like the wavelength of this modulation. So in the limit where you take q to infinity, it becomes, in the limit where you take the modulation wavelength to infinity, where q goes to 0, this basically becomes like a rigid rotation. And the whole point is that we have a circle of degenerate states, so that costs no energy. So this gives you the intuition why we should have, once we have a continuous symmetry, we always have a mode that disperses from 0. Okay, so this is called Nambu-Goldstone theorem. It's a very deep and important concept okay. The second thing we're going to establish is that such a spontaneous symmetry breaking in a quantum system is only possible in the thermodynamic limit. Okay? And we will establish this through something called the Anderson's tower of states. Okay, so what we're going to see is that if you have a finite system, okay, then the ground state, you see, imagine that I give you a double well potential, okay, and I initiate a particle at this minimum. What do you expect it to do with time if I evolve it quantum mechanically? What do you expect will happen?
From the
Yeah, I started as a delta function in this potential way. Well-defined location. What's going to happen as a function of time?
it will disperse.
It
but
will spread.
It will stay. Most of its value, it will have a peak there, but it will also have a smaller peak here.
And that's it?
Oscillate.
It will stay, it will oscillate. It will actually oscillate back and forth. Okay, it will tunnel. Initially, you're right, after a short time. So here there is some matrix element gamma, which describes the tunneling. And if you look at times that are much shorter than 1 over gamma, then you're right. You're going to have most of the weight here. But if you weight gamma time, it will actually be the exact opposite picture. It will have most of its value here, and it will go back and forth. And the ground state of this system, as you know, is actually an even. The eigenmodes of this potential are even and odd superpositions of the two sides. So, and the same concept is related to this number 2. That, you know, what do I even mean spontaneous symmetry breaking? We're talking about a quantum system. Quantum system is going to be, the ground state is going to be some superposition in the same way that actually tends to restore the symmetry. So you see that quantum mechanics naturally restores the symmetry. So you can ask, how can a quantum state even break a symmetry spontaneously? This happens in the thermodynamic limit. And this is what we're going to discuss there. Okay? So that's the second thing we're going to establish. Each one of these very, very deep concepts, and we can learn a lot from them. It's very important. Okay? And the third one is that condensation of a boson, bosonic field, implies what we call off-diagonal long-range order. Okay, which is off-diagonal long-range order. Okay, so what that means is that the correlation function A dagger of R, A of R prime, okay, in the limit where you take the distance between r minus r prime to infinity, actually goes to the condensate density. Okay, and it means that there is some phase. It means that there is phase coherence, which is long ranged. Okay, so in the language of what we just discussed, it means that the angle theta at some position and the angle theta at a very different position is going to be, it's going to fluctuate, but it's going to fluctuate around the same value. And this is very important. This implies, so ODL RO implies what we call phase coherence. Okay? By the way, I should mention that the fact that we have a linearly dispersing mode also implies rigidity. And from here, we can understand that this is phase rigidity. This phase rigidity is exactly what is going to allow the superfluid to carry a current. Yeah, maybe I'll add a fourth point. Originally, I was supposed to write it in point 2, but maybe I'll write it here. The linearly dispersing mode in this case implies phase rigidity. Okay, means that the phase at different positions it's kind of like elastic. You can imagine that if you try to twist the phase somewhere, it wants to go back. Okay, it sticks together. This is, by the way, the difference between a Bose-Einstein condensate and a superfluid. A Bose-Einstein condensate doesn't have any interactions. All these particles don't know about each other. They just all collapse into the ground state. What that means is that maybe they sound, or you associate them with a superfluid, but they're not really a superfluid until they interact. Because if they don't interact, they don't have this rigidity phase. And we're going to see later that without rigidity, there is no superfluid motion. All the beautiful properties of a superfluid, okay, implies phase rigidity, which means the superfluid can carry a dissipationless current. And here we're going to discuss what is known as Landau's criterion. Okay, so the main reason I wrote all these things on the board is because I want all these concepts to, first of all, that you understand what we're going to establish. Okay, all the deep concepts that we're going to establish, and also to make you acquainted with the terminology. Okay, so Nambu-Goldstone theorem talks about the fact that if you broke continuous symmetry spontaneously, okay, there is a linearly dispersing mode which reflects the rigidity of the order parameter. The fact that this spontaneous symmetry breaking is only possible in the thermodynamic limit, i.e. in a large system containing a huge amount of particles, and this we're going to establish through this concept of the Anderson's Tower of States. Specifically, if the symmetry breaking is of the superfluid type, where a Bose liquid condenses, that also implies off-diagonal Lagrange order, which actually means that this rigidity is phase rigidity, phase coherence. And the phase rigidity is actually exactly the property that endows the superfluid with its beautiful properties such that it can flow without dissipation. And this we're going to establish through what we call Landau's criteria. So let's start to do these one by one. So the first thing we're going to do is we want to obtain the low energy effective theory of the broken symmetry state. And there we will see this linearly dispersing mode, this guy. Okay? And this is called the XY model. So what we're going to do is we're going to write our field. We're going to expand it around the ordered state. So we're going to give it this rho naught. I remind you that rho naught is mu over v naught. Okay? I'm assuming that mu is positive, and therefore rho naught is finite. And then I'm going to give it some small fluctuation, delta rho. Okay, and then I have another degree of freedom, which is what?
Gauge.
This, right, which means that we're allowed to add a phase. Okay, so now I just plug this in the original action. Okay, assuming that delta rho and theta can both depend on space and imaginary time, then what you get is something like this. So I'm assuming that, first of all, I'm throwing away constants and total derivatives are boundary terms. So let's assume for a moment, not think about boundaries and neglect them. Okay, this is clear? So just plug this in. Okay, that's true, let's see. Okay, so if you remember, when we derived the field theory, I taught you how to identify who is conjugate to who. Do you remember that? So now we have two fields, delta rho, right? Delta rho as an operator is A dagger A, right? Minus rho naught. Okay, and theta I don't even want to write theta as an operator. There's an equivalent operator theta, which we can also write. But this delta rho field is associated with, and we also have theta, whatever it is. Okay, so we have these two fields now. How do I know who's conjugate to who? This is the question. Do you remember that? Maybe I'll ask you, what is the commutation relation between delta rho and theta as operators?
It should be 1.
Who said what?
It should be 1.
1? That's close. You know that when
I.
Nice.
Like a momentum and position.
Yes, exactly. They're like momentum and position. Exactly. So one way to, so this theta here, you can think about it, let's assume that we're in the space of theta. Okay? So this will be like a derivative, if you like. Yeah, then you know that e to the I theta naught delta rho a e to the minus I theta naught delta rho is indeed e to the minus I theta naught a. So you see that delta rho is the operator that generates a phase shift to A. Okay, so that's maybe a way to understand this. And this is I, by the way, because of this I here. So if you remember, we had, maybe I'll write it, it'll be clearer if I write it like this. We have delta rho d tau theta. Okay? And beforehand we had psi bar d tau psi, right? And then the commutation relation between A dagger and A was indeed 1. But now we have I, so like Yuval said, it's I. Okay, good. Now the next step is, let's integrate out delta rho fluctuations. Okay? So let me for a moment describe what I'm doing. So I want to remind you that we're talking about this Mexican hat potential, okay? So we have, maybe it's not, it's not, how do you say, appropriate, it's not politically correct to say Mexican hat potential, especially if you have a Mexican in your class. But luckily we're in Israel. So we have this Mexican hat potential. Looks something like this. Okay. I don't know if you kind of get my drift. Okay, so this is the potential. And then we have two types of modes. There are fluctuations like this, which are theta. And there are fluctuations like this, which are this delta rho. Okay, these are the two fluctuations. Now, you can identify that the fluctuations theta are very different from the fluctuations delta rho, right? Delta rho is massive. It has a mass. Theta is soft. You understand that concept? Is that obvious? So, delta rho, right? If I anticipate that there's a term like m delta rho squared. And indeed I see it. Here it is. And this is exactly this. The fact that that if you move rho from its minimum value, from its symmetry breaking value, you add a delta rho, you immediately go up in energy. quadratically. But if you change theta, that doesn't cost energy. It only costs energy if it's through a derivative. Okay? So this is the logic. Now this is a very common thing that you do in field theory. If you have a massive mode, you integrate it out. It just normalizes your low energy theory. So if you like, we're looking at the physics at energy is much smaller than this mass. Now this term is called the Higgs mode. Higgs mode. Okay? And it's actually not related to what is known as the Anderson-Higgs mechanism, what we will learn, but it's called Higgs mode. And this is called the Goldstone mode. Or maybe Nambu Goldstone mode. Okay? So what we want to obtain is the action for the Nambu Goldstone mode, and therefore we were going to integrate out delta rho. So how do we do this? You see that the action is quadratic in delta rho, so it's very easy. We just need to complete the square. Okay? So what we have is, so I'm writing delta rho and theta to integrate out delta rho fluctuations. We complete a square. That's almost all you do ever in physics, complete a square. Right? Yosef, that's what you're doing now in your research? So if I complete a square, I get delta rho plus I theta dot divided by 2 times V naught over 2 minus Laplacian of 2m rho naught V naught minus the Laplacian of 2m rho naught delta rho plus I theta dot divided by 2 times V naught over 2 minus Laplacian over 2m. Okay? And then I have plus theta dot squared over 2 V naught plus rho naught Laplacian of theta squared. Now here I cheated a little bit because I wrote the inverse of a derivative, and that's of course a kernel. That's some non-local term. But assuming that everything is changing slowly, we can neglect these kind of derivatives and just perform this Gaussian integral, which is not that difficult to do. It gives us some determinant. So we'll renormalize our action, but the end result. Now, okay, let me write. Now, integrate out delta rho, which is a Gaussian integral, and then what we obtain is the integral from 0 to beta d tau d dx. We get d tau theta squared d tau 1 over 2 v naught d tau theta squared plus rho naught over 2m grad theta squared. Okay? So this is the XY model. And we can obtain the velocity from the equations of motion. So we write delta S to delta theta, which gives us minus 1 over V naught T squared tau minus rho naught over M Laplacian times theta equals to 0. If we take tau to minus IT, which is going back to real time, this becomes dt squared minus rho naught V naught over M. This whole thing is Laplacian times theta is equal to 0. Okay, now this implies that the velocity is, right, it's the square root of rho naught V naught over M. Now I want to go back to our solution. So I want to remind you that EK that we obtained in the beginning of this lecture was square root of k squared over 2m times k squared over 2m plus 2 times rho naught V naught, which at small k is exactly square root of rho naught V naught over m times k. Okay? So the velocity of these phase modes is indeed the linear velocity that we obtained from the Bogoliubov quasi-particles. But now we have a much deeper understanding of what these modes represent. They represent a gapless mode associated with global gauge invariance. So if we make a gauge, we make something like a gauge transformation, but instead of doing it globally, we change it very, very slowly in space. It's very close to a global gauge invariance, and therefore it costs a very small energy, and this is exactly this linear spectrum.
Can you explain what you mean when you say mode?
Well, this is a wave equation, right? So there's a field, okay, which the low energy excitations of the theory, you obtain suddenly some field which its equation of motion at low energy looks like a wave equation. So once I have that, this is what I call a mode, if you like, because it's how can I explain? It's like a free particle. It's like an effective free particle. It's a terminology, I don't know, it's not crucial. What's really important is that you understand that now we have this, the phase, we have like a phase, it's rigid everywhere, and if you create like a perturbation, it just propagates like waves. And the velocity of these waves is this parameter.
Okay. Also, for the equation of motion, shouldn't we use the Lagrangian? Why do we use the action?
I don't understand. It's the same thing. What's the difference? The action is an integral over the Lagrangian.
Over time.
The equations of motion
Mm-hmm.
you're talking about the Euler-Lagrange equation. Euler-Lagrange you can obtain. I'm sure that when Avi taught you Euler-Lagrange, he showed you that you can obtain the Euler-Lagrange equations as a variational principle. Basically, a minimal energy or minimal action principle. So this is precisely the minimal action principle.
Okay.
Right? Okay, any other questions?
Why it's called the XY model?
It's called XY model because, okay, so this model emerges in many different systems. Okay? One of them is, imagine that you have spins. So if I write, let's assume that I'm thinking now about a classical spin model. Okay, so I'm thinking about spins. So you know, by the way, how to. So if I write a Hamiltonian, which is something like minus J S I S J dot. This is called the Heisenberg model. Good. Now, what defines whether this model is classical or quantum? You know?
Spin classic.
How do you make a classical spin? What do you think about?
Polarization.
No, but in terms of to make this quantum, okay, I could put these S to be like sigma x in the x direction plus sigma y in the y direction plus sigma z in the z direction. This is the most quantum possible.
Mm-hmm.
Okay? But if I would want to make it classical, what would I do?
Oh, it's only Z. Only sigma Z.
That's one way to make it classical. So you can make, but that's an Ising model. But say I want to write a Heisenberg model, I want to make it classical. How would you do that?
Using plus and minus 1.
What?
Using plus and minus 1.
So this, what? Whoa, sorry. This is dangerous. What are these Pauli matrices? What are they? What do we call them? We're sophisticated,
A basis.
smart asses. What?
A basis.
No.
SU2.
What are they for the SU2 group?
סיבוב.
They are the generators of the SU2,
Right.
right? But they're not just the generators for the SU2 group. They're the generators for the SU2 group. They're like the minimal, how do you call it? There's a name for that. Minimal representation or something. Because they are J equal to 1/2.
Right.
Or L equal to 1/2. Okay, they're like half integer, lowest possible. You can have L equal 1, L equal 2, L equal 3, right? You can increase the angular momentum. Now, if you increase the angular momentum more and more and more, so say I look at angular momentum. So here, these spins, if they're Ising, they can only be up or down.
Right.
2 states. If I take L equal to 1, how many states do I have? 3. I have 1, 0, minus 1. Okay? What happens if I take L to infinity?
To infinity plus 1. Infinity.
What happens if I take L to infinity and beyond? But what happens at infinity? Seriously.
It became discontinuous.
Yes, exactly. They look like rods. They basically become rods.
Mm-hmm.
You just look at any direction. So instead of looking at, and also you'll find that their commutation relation becomes weaker and weaker and weaker. They're non-trivial commutation relations. Basically, the limit where you take L to infinity, this model becomes classical. Now in this classical model, I can actually break the symmetry. I can do something like, so this is Heisenberg point, but I can break the symmetry. Imagine, for example, that I write a different model. I write JZ sigma SZ plus, minus J perp SX plus SY. Okay? And let's assume that this guy is bigger than this. J perp is bigger than JZ. What does it imply? It implies that these classical rods want to be in the plane. And they're coupled to each other. They want to be ferromagnetic. They're basically like our face. Right? They're like a clock. At every location in space, you have like a clock. And they want to look all in the same direction. So in the ground state, they have a degenerate minimum, which is like a ring. And the ground state, they're all going to point in the same phase. And if you take one of them and you rotate it, there's going to be like waves that are propagating. And these waves are going to look like this. And this is why they call it XY model. Okay? And it's very generic. It appears, basically, it's related to the fact that we broke a U1 symmetry, continuous U1 symmetry. For us, it was the phase, but it can be anything. You break this U1 symmetry spontaneously, you're going to get a linearly dispersing Goldstone mode, and the low energy effective theory is going to be XY mode. This is what you should anticipate. Yeah, it's also useful for future applications to identify what is density and current. This is actually pretty important. So let me do a shortcut, but J naught. So remember we have this current J mu, this Nater current. So J0, okay, is basically like I rho naught plus delta rho, right? Okay. And and here I want to remind you that, right, imagine that I write a Lagrangian, which is P Q dot minus H, and then I kind of perform the Legendre transform, right? Then I'm going to get L, which is Q dot squared over 2 maybe, minus, minus H. Yeah, maybe we can write something like P squared over 2M minus Q squared. Let's write it like this, okay? Just as so here we're gonna have minus Q squared over 2. Okay, so this is like the harmonic oscillator. Now, why am I writing this? Because you see that when you do a Legendre transform like this, what's associated with the conjugate momentum is Q dot. So it won't surprise you that this guy, J naught, is just I d tau theta. So basically, density in the XY model, density is associated with the time derivative of theta. Okay? So this is, if you look at this action for a moment, this is just a harmonic oscillator action in imaginary time. Okay? In imaginary time. This, this is the field Q, if you like. Just instead of Q, we have gradient of Q, and its conjugate is d theta tau. So that's one thing. And then the second thing is that J, okay, which we can write, maybe I should have written it. You can take all this, so this is I over 2M psi minus psi grad psi. Here it's easier. Here I don't need all this intuition. You can just plug in the definitions we use. and you find that this is rho naught over m, rho naught over m, why the 2m? Grad theta. I think there's no 2 here. Maybe there is a 2, but here there is no 2. Okay, so what you see now, this is very, very important. So I remind you that this J mu is the current associated with number conservation. So this is number current. So this is the charge. Gradients in time are charge. So if your charge is, so now you can imagine that you have something like this. This is imaginary time. Imaginary time. And this is space. Okay? So if I have some time dependence here, that basically means that there is charge there. Okay? So let's say the charge is changing as a function of position. So let's start from this configuration. Okay? So everywhere this, so now I'm thinking about this theta like a clock. Okay? This XY model like a clock. So let's say everywhere this phase is the same. Okay? That means that charge and current, there is no current, and charge is uniform. Now let's assume that I start to modulate this. So here I have something like this. So there is time dependence here of tau. This implies that locally there is charge here. At this position in space, there is charge. There is time dependence. Okay? Now, what happens if I have
The charge being the number of particles?
Yes. Now what happens if I now have something like this? What does this imply? This means that throughout time it's not changing, so the charge is uniform, but it's changing in space. What does that imply?
J.
It implies a current. So it should surprise us, but in the superfluid phase, in low energy, currents are generated by gradients of the phase. Okay? And generally, what you have is that everything is kind of fluctuating. So you have charge fluctuations and current fluctuations described by just generic configurations of this. And everything is kind of rigid. It doesn't want to have modulations, but it will have some fluctuations because it's quantum mechanics. Am I out of time or something?
So
how much more time do I have?
20 minutes.
20 minutes?
Can we do the same, exactly same model, but instead of using four, like 3 real Euclidean dimension and 1 imaginary with Minkowski metric?
You're asking if you can do this in real time?
Yeah. But
Yeah, you can analytically continue this. It's exactly the same model in real time. But the fluctuations have a different meaning. So it's okay. So what? Sorry, I take it back. What exactly do you mean? You want to write? You want to ask what would be the? Because what I can do is I can interpret. Okay, so you have to remember what we did here. So what we did was we wanted to compute the trace over e to the minus beta h.
Right.
Now, if you do analytic continuation, you have to explain what exactly you're computing. Because then it's like evolving in e to the I h t,
Right.
and then it depends on like the initial state you started from, and it's a different question.
Okay.
But you can, maybe we will discuss that later, you can extract real-time quantities from this imaginary time. And one of them we did exactly here. So the equation of motion, for example, is one of the things you can read out of this field. Okay? Okay. Blah, 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 blah. Finite velocity reflects rigidity. Okay, so now let's talk about rigidity. Okay? Let's talk about Landau's criterion and phase rigidity. So basically what we established here is that breaking a continuous symmetry means that there is a linearly dispersing model. Okay, this is the XY model. Let me see if I miss something. Okay. So, I want to make an analogy between a superfluid and a lattice, a crystal. So what is a crystal? A crystal is a situation where another continuous symmetry is broken, but this continuous symmetry is not global gauge invariance. It's what symmetry is broken? Translation. Translational symmetry. Now you can imagine you can imagine that I can associate each line here with a phase. So let's call this, so I can write this, imagine that I write this crystal, so let's say this is like Y direction, and this is like X direction, okay? So I can describe this crystal with something like a cosine of QY plus some phi plus cosine, I can probably even write it. I can multiply them, qx plus phi. So my density could be something like this.
This.
So
Q.
Q is integer, right?
Q is the wavelength.
Okay.
So this whole thing, let's call this phi y, and this let's call it phi x. So what these lines actually mean, this is like phi y equal to 0, this is like phi y equal to 2 pi, this is phi y equal to 4 pi, this is like phi y equal to 8 pi, and so on and so forth. Now imagine that I create shear, okay? Imagine that I apply a force in this direction, okay? But I apply it on this side of the crystal, and this side is held fixed. What will happen to the crystal? Yes, exactly. So what you're going to have is the atoms are going to shift. So the new crystal is actually going to be, it's going to be shifted like this. Okay? Okay? It's going to be slightly shifted, and we can describe this by taking, let's call this phi y and this phi x. By taking phi y to be some a x. Okay? So in other words, the gradient of phi y is equal to a x hat. Okay? So phi y is changing as a function of x. This is x. Okay? Now, what's special about... okay, so now let me make this analogous to a superfluid. So imagine that I have like a tube with superfluid in it. And here I have theta equal to 0. And here I have theta equal to... so this is like length L. So here I have A times L. Okay? So this means that, you know, basically my phase is slowly rotating. And we know that this implies a current. A current is flowing in this direction. Okay, now you can gain a lot of intuition from this analogy. Why? Because it kind of tells you how this will respond by using your day-to-day intuition for this. What happens to a crystal if I push it like this? What is it going to do? After I let go, for example, what is it going to do? It's going to come back. This is what we call elasticity. It's elastic. This atom here, let me plot them. This atom here is coordinated, right? So for example, this atom here in the center, it's coordinated with its surrounding atoms. So it knows that this is its partner. Even if I push very strongly, you see, and it reaches the same line as this guy, if I didn't break it or something, then it's basically going to come back. This is what we call elasticity. And the same thing happens with a superfluid. So if you try to twist it, it's kind of rigid. First of all, you kind of feel some rejection, but it also maintains its order. So you apply a current, but it stays ordered. Now, here in this point in the course, I like to tell a story that when I was bar mitzvah age, my parents took me to a trip to Kenya. And I told my parents that I want weapons. The Maasai, I don't know if you know what the Maasai are. The Maasai are it's a tribe in Kenya and Tanzania. They are well known for, they're very tall, they jump very high, so for sports they are well known in like sports. But traditionally they live in a very weird fashion, like they have houses made of cow dung, they drink milk with blood of cows. They basically live off cows, but they're also known as warriors. They have spears, and they're very good with metal. They have these spears. And I told my father that I want a spear like that to bring home as a memory. And my father, for whatever reason, he's also a scientist, and he knows a thing or two about science and matter, material. And for whatever reason, he decided he wants real spear, not fake. So we started walking around in the Nairobi market, and every day he would say, "Is this a real spear?" And the seller would say, "Yes, yes, of course, it's real, it's genuine." And he would take it on his knee, bend it, it would bend, stay bent. He would say, "No, this is not real. Take it away." And like this went until we found one that was real, and he bought it, and we still have it in our house, hidden somewhere, because it's so dangerous that we never ever opened it. We did it. I don't even know why he went such a crazy thing. It even smells from blood. It's like insane. But the question is, why does it happen that, when the fake... First of all, let me ask you, do you know what's the difference between the fake one and the real one? Can you guess? What's real about the real and fake about the fake?
The real has more
The molecule.
carbon in it. It's something.
The real has more carbon in it. Good. Why?
It helps it
Maintain its elasticity.
and bring the iron atoms closer together.
No,
The
not.
liar is like graphene or like.
It's the difference. It's because the real one is made out of steel, and the fake ones were made out of just iron, plain iron. Now, what happens in iron? I'll tell you. So, what you have in a real crystal is you have defects. It's not like this. You have, for example, dislocations. So you can imagine that your atoms are like this. Okay? And then so basically you have something like this. Okay, so you have this thing here. It's called a dislocation. Okay, and if you go in a round trip around this dislocation, you will find that this phase. You know what? I don't like the way I wrote it. I shouldn't have written it like this. I should have. Let me fix it. I should have written it like this.
Because it's 5.
No, it's just wrong. So this should be something like rho naught cosine. Sorry, I just made a mistake. R plus phi. There's actually only one phase, and then phi is equal to A times x. X, and therefore grad phi is Ax hat. This is actually the right way to write it. So please correct that in your notebooks. If you go around this thing, you'll find that this phase phi, you see, basically you can interpret each one of these lines. Look at these lines here. Each time I cross a line, it's another 2 pi, right? So you can interpret each one of these lines as 2 pi. But if you do a round trip, here you get 2 pi, here you get minus 2 pi, here you get minus 2 pi, here you get 2 pi, so overall it's 0. But if you go around this guy, you get 2 pi, minus 2 pi, here you get another minus 2 pi, and here you get nothing. So this is a minus 2 pi, it's basically what we call a vortex. So the phase phi is actually winding around this thing. Instead of being fixed everywhere in space, it's a configuration where the phase is doing that.
That has to do with parallel transport.
It is. It's actually what we call a Berger's vector. It's less related to parallel transport. You can think about it. Yeah, actually, you can think about this as some curved space, discrete curved space.
Right, with a topological...
Yeah, you can think about it. But, okay, I'll tell you what, the point is that there are other defects that are related to curvature. I think that this defect actually doesn't induce curvature. We can discuss that later. But the point is that this is like, now what happens?
This is like in nonlinear dynamics when you do this one trip around and the amounts of turns the vector that you can from plus to minus. This is the amounts of defect inside the tree that encloses it, right?
True. So basically, this is like a winding number. This is vorticity. So this is what we call a vortex, and the number of vortices you have inside a loop is the amount of vorticity by Stokes theorem. Okay? So it's not different than that. Now, what happens when my father bends the metal? What happens is that these defects, they run. They change location. And once they change their location, they arrange themselves in some minimal energy for the new bent situation. And then they get stuck there. And that's what you have. Now, what happens with carbon? So when you add carbon, it creates pinning sites. It's pinning sites where these vortices pin. And therefore, if you don't overcome the spinning energy, the vortices don't move. They stay stuck there. And then it goes back to its original situation. Now, the same thing happens with a superconductor. You can imagine that if you induce... Now, what happens when you overcome a certain threshold? Over a certain threshold, you'll start having these vortices, penetrate, come in, and the system will break down. So if you shear this strong enough, eventually, no matter what, you're going to start creating these out of nothing. They'll come out of the edge. And there was a student here that reminded me that when I teach Math 3, I talk to them about tanks, about the fact that the Russian scientists understood that if you want to penetrate a tank, you need to create a gas burst that is faster than the speed of sound in the material. And this is exactly the point. So what we're going to see in a moment is that when we overcome the speed, the critical speed, we start breaking basically this rigidity, and the superfluidity will break down. And this is Landau's criterion, but I think I'm out of time. So next class, we'll see that actually this velocity that we see here is actually a maximal velocity that this superfluid can carry. Below this velocity, it flows without friction. Okay? But above this velocity, something critical happens and you start generating these Bogoliubov excitations. So you can imagine that below the threshold, it flows around defects, around the perturbations, without creating any excitations, and therefore it doesn't have anywhere to dump energy or dissipate anything. Once you go over the threshold, you start generating these Bogoliubov excitations. And what's special about this compared to a free gas, which would be a BC, for example, is that the velocity is finite. So for a BC, V0 is equal to 0. It means that the critical threshold is 0. It means that it immediately dissipates. So it can't have a superfluid just because it has no rigidity. Okay? Thank you.